Okay, hello class. This is my video presentation on 3D particle equilibrium. First of all, I chose to do my video presentation on 3D particle equilibrium because, in my opinion, it is one of the most important takeaways, not just for this class, but for engineering as a whole. And learning how to observe things in 3 dimensions is something that will be really useful in our futures. Okay. Now to begin, these structures are not moving. When an object or structure is not moving, that means it is in equilibrium. In this case, it's static equilibrium. It's staying stationary in the position it lies in, for both this crane-looking thing and this traffic light. This occurs because there is no acceleration. Can you write that? No acceleration. And because there's no acceleration, that means that the forces acting on this traffic light and this fishnet are equal to 0 in all directions. So the forces in the x are equal to 0, forces in the y are equal to 0, and the forces in the z are equal to 0. Because we're in static equilibrium and there is no acceleration, the force exerted on this traffic light and this fishnet will be evenly distributed throughout the entire structure in order for them to equate each other. In 3D, we have this idea, but in 3 dimensions. And in the 3-dimensional coordinate plane, x, y. A good example of this is this crane here. Now, the structure and the forces of this crane exist along this coordinate axis here. The force of tension, force 1 of the chain, force 2 of the chain, force 3 of the chain exist along this coordinate axis here because of 3D. In fact, I actually did a diagram of the crane to make it easier to visualize or maybe explain. Okay, if I get it to normal size. Yeah, got it. Okay, now the force that is holding the entire structure or the entire weight of the structure is the force of tension here. And force 1, force 2, and force 3 are the ones holding this metallic plate here or this piece, whatever you want to call it. Now, particle equilibrium is occurring along point A. Since there is no acceleration and we are in static equilibrium, all the forces that happen along point A are going to have to sum up and be equal to 0. This means that the force has to be equally distributed throughout the entire structure. And this means that if you sum force 1, force 2, and force 3, it will give you the force of tension, which is opposite to these forces here. Forces. Okay? And now, since we are in static equilibrium, the sum of all these forces of force 1, force 2, and force 3 are going to be equal to 0 in all directions, in the x, y, and z direction. Okay. Force of x is equal to 0, force y is equal to 0, and force z is equal to 0. These equations are known as equations of equilibrium. And we use them when we have no acceleration. No acceleration. That means summing the components of force 1, force 2, force 3, and the tension in the x, y, and z direction are going to give us 0, or have to be equal to 0. The cool thing is that when we know the force exerted on the structure, we can find any other force acting on it as well by using these equations of equilibrium. That's it. All our forces equal to 0. And let us solve for the force of our choice. Okay, just to clarify a little bit, I believe I said the sum of force 1, force 2, and force 3 together are again equal to the magnitude of the tension. But that doesn't mean that force 1 will have the same magnitude of force as force 2 and force 3. They each have individual forces. Sometimes they can have the same force, but that isn't always the case. And also, since we're in static equilibrium, we got to sum the components of force 1, force 2, force 3, and the tension to be equal to 0. That's something I also forgot to clarify. I hope that is fixed. Alright? Okay, so before I solve any problem in 3 dimensions, first I want to talk briefly about position vectors and unit vectors, because these help us solve problems that are in 3 dimensions. Now, what a position vector does, it locates a point in space in 3D. It locates it along 3 directions, along the x direction, y direction, and z direction. Notice how we have 4 in the x direction, 2 in the y direction, and -6 in the z direction. And that is a vector here, which locates a point. Also, with the position vectors, you could find the magnitude by using the distance formula over here. Now, what this is going to be useful for in my example video is when you have, let's say, a force that goes along a beam or a rod or maybe a rope. You have a force, but how do you find the components of that force? You find that by using the position vector over the magnitude of the position vector. Or you could say the distance here. As you can see, I have my components 2 meters in the x direction, 4 meters in the y direction, and 6 meters in the z direction. Here, all that is over the distance here. Now, once you have the distance, you will use this formula to find the unit vector. What this unit vector does, it gives us a direction. I'm going to write that down. It gives us the direction. And once you have this unit vector, you will multiply that times the force to find the components of the force. Force f of x, fy, and f is z going along this rod here. Okay. Now I'm going to solve a problem involving 3D equilibrium, or 3D equilibrium problem, however it is said. Now, to solve these problems, these types of problems, you always use 2 things. You should always use a free body diagram and equations of equilibrium. So, equations of equilibrium and a free body diagram. Okay, now this reads, the 3 cables are used to support the 4 kilogram flower pot. Determine the force developed in each cable for equilibrium. Nice. Okay, now we have to analyze these forces here. The force of tension, AD, force of tension, AB, force of tension, and force of tension, AC. Oh, I cannot forget about the weight of the flower pot. Right here. These are the forces we will analyze. For this problem, I'm going to use a vector approach to solve for the tensions, because I just think it may be easier. Now, before I solve this problem, I start by stating my knowns and unknowns. So, state my knowns and unknowns. First, okay, so my knowns. I have the weight of the pot, which it was said to be 40 kilograms times the gravity here. Oh, by the way, for your free body diagram, if you want, you could also use this same image you have here. You don't always have to draw for your diagram. So just saying that. Okay, unknowns have tension AC tension AB, and tension AD. Okay, so my plan with this is that I plan to resolve my tensions, forces into components, so I can apply the equations of equilibrium. I'm going to go ahead and write that down. It will resolve my tension, forces into, so I can apply equations of equilibrium. Now for this problem, I'm going to begin first with tension AB and tension AC, also with the weight, because these are easier since they exist in one direction. Now tension AB, vector rotation is 0 in the I hat, 1 in the j hat, 0 in the k hat. Okay, so notice how you only have 1 in the j hat. That's because this only exists in the y direction. That's why. And tension AC, it will exist in the x direction only. So you have.
Sorry, I missed that. Could you say it again, please?
Sorry, that was Siri. I was talking and Siri thought I said something. Okay, now back to the problem. Okay, 1 in the I direction, 0 in the j direction, and 0 in the k direction. And as for the weight, it is only existing in the z direction, so the weight gets the same treatment. J direction and 1 in the k direction. Okay, right here. Now, I already wrote my components for tension AC, tension AB, and the weight of the pot. Now, for tension AB, this requires probably a free body diagram drawn out because it may be harder. So, for tension AD, I will make a free body diagram. Sorry, I'm back. My voice died halfway and I had to get some water. So I was about to solve make a free body diagram for the tension here. But before I move on, I actually made a mistake here. So this is the weight in the negative k direction. 1 meter in the negative k direction. Here's 1 meter. This is 1 meter also in the j direction and 1 meter in the x direction. Just had to correct that. So anyway, here's my free body diagram of D to A. So I'm going to make a 3D coordinate axis here. Okay. Point D. Point A. I believe the distance was 1.5 meters. And 2 meters in the y direction. This is y, x, right? And it was 1.5 meters in the z direction. Now, connecting these two. Now, I'm going to solve these for the components of the tension AD using position vectors, because my end goal with this is to find the components in the x direction, y direction, and the z direction of the tension. So the point along D is 0, 0, 1.5 meters. Since it's acting only on this pole here, and it's not anywhere in the x or y coordinate, only the z coordinate. A has points 1.5. Has 2 meters, and has 0 meters in the z direction here. Okay, now since we want a position vector, we actually have to do some vector math. So we're trying to find the point from A to D. So we do that by subtracting the vector D from A. So it will look something like this. 0, 5 minus 1.5 meters, 2 meters, and 0 meters. Almost ran out of space there. Okay, so AD will equal, it's gonna do this here. 0 minus 1.5 direction. I should really get more space here. Do the problem. Okay, plus 0 minus 2 meters. I'm leaving the units off here because I already mentioned them. Plus 1.5 0 and the k. Now that's gonna sum up to give us this negative 1.5 I, negative 2j, and 1.5 in the k here. Okay, now to obtain the unit vector, we have to use this equation. The unit vector, which gives us the position. The direction. If I could correct that. And that is the position vector over the magnitude of the position vector. Here. So that means the magnitude of RAD will be equal to 1.5 squared plus 2 squared plus 1.5 squared. Yeah, by the way, these values here are negative, but since I'm putting them in square root, they're just going to cancel out anyway since they are multiplied, or they're raised to the power of 2. So that's that. And now putting this into a calculator, it gives me 2.92 meters. And that makes our unit vector be all of this. I should just, copy paste that. Duplicate. That's much easier. Over 2.92 meters. Yeah. Okay, and now what I'm gonna do, I'm gonna multiply the tension force times this unit vector. So I can obtain the components of the tension TAD. I'm gonna write that down. I will multiply the force TAD, sorry, by the vector to obtain components of in the x, y, and z directions using this equation here. The force times the unit vector. And that looks like this here. Tension AD times the unit vector. Now, that's going to look like some of the forces of tension AD will be tension AD over the magnitude of the position, which is 2.92 meters, and I have negative 1.5 meters in the I. Just take the units off. I have negative 2 in the J, and I have 1.5 in the K direction. Okay, now we have the components of all the forces. The components of tension AD, tension AC, tension AB, and the weight now. Now, since we have all the components, I'm gonna use equations of equilibrium. Because there's no acceleration and whatever we're working with is not moving and is in static equilibrium. So I'm gonna write that down. I have the components of the force in directions. Now I solve for the tensions. D, AB, and AC by using the equations of equilibrium, because there is no acceleration. And I want to solve for the tensions as well. Oh, I already said that, so just disregard what it said there. Okay, now what I'm gonna do, I'm gonna use these equations of equilibrium here. So sum all the forces in the X to be equal to 0, all the forces in the Y to be equal to 0, and all the forces in the Z to be equal to 0. That is going to look like in this here. So, okay, I should probably need more space because I'm going to need the space here. Okay, tension AC in all directions. Oh, just like, sorry about that. I made a little mistake here. Okay, now from the previous answer we got tension AC only exists in the X direction. So tension AC, and it's in the positive X direction, by the way. Same as, okay, we have tension AD over 292 times 1.5. Yeah, by the way, this is negative because of the negative here, and also because it's in the negative X direction. So there is that as well. And that's going to be equal to 0. Now along for the forces in the Y. I could probably fit here, yeah. Okay, now we had from up here, tension AB exists in the Y, minus tension AD meters times 2. That will be equal to 0. And lastly, we have the forces in the Z direction. So that's going to be okay, 1.5 tension AD 2 meters minus the weight equals to 0. The force of this weight here, or the force due to weight, is going to equal the 40 kilograms we had times 9.8. And that is going to be equal to, I think, putting that into the calculator, 392 newtons. Okay, now for this, since it's not so hard of, or these equations aren't that hard to solve, I'm just going to do them by hand. So, Okay, I'm starting off with this one. All we gotta do is just set that equal to the weight. Here, 1.5 tension AD, 2.92 meters. Okay, then okay, now since I solved for tension AD, I could plug tension AD into this equation here so I could solve. Yeah, convey tension. Oh, by the way, I'm moving this this tension to this side here because we have a negative and now we can make a positive. So that's the reason for this being here. And that's going to be equal to 2 points. Okay, same thing goes for this one here. Okay, I'm gonna plug that in, and tension AC will give me 392 newtons. Okay, so these are our answers. Tension AD is going to be equal to 762 newtons, tension AB is going to be equal to 522.4, and tension AC is going to be equal to 392 newtons. That's the force along each of these cables that each of these cables have now. And that force is, and the force of the weight here is evenly distributed throughout these entire tensions here. Okay, I am finally done, and I'm glad I'm done. Alright, goodbye.